Hey guys, and welcome to our day 15. Today we're going to continue on with electricity by talking about Ohm's law, what should be a little bit of a review, but we're just going to go in from the beginning. So first, let me explain what you're going to do today, and then after that, if you would like to stay tuned, then I'm going to go through just a couple, I promise, not the whole thing, just like a couple slides about what to do or how this relates to each other. So, your attendance assignment for the day. I was just kind of tired of doing Google Forms, so I pulled out the very nifty game that my parents got me for Christmas 7 years ago, Would You Rather? And I tried to find fun ones, which was, it was fun with me and my husband, I guess. So, I have 3 Would You Rather questions. You only have to pick one, please, and then say which one you would choose. If you try to support your choice, it's just always more fun. I'd like it if you guys could comment actually on the assignment. That way your classmates are kind of interacting with each other. But if you want to put in a private comment, that's fine too. If you're, I guess, not really into games in general, or if you just want to be a real stick in the mud, or if you're just feeling a little overwhelmed by all these would you rather choices, then you can also just comment here, and that's good enough for me. We're at the home stretch. We're making this easy peasy. After that, we have a PhET lab. Woohoo for PhET labs. This one is on Ohm's law, which again, as I said earlier, should be a bit of a review. This is a graded assisted assignment, so it does go in the grade book, but I honestly don't know how it could go wrong. I say that like with a grain of salt. Please don't, try your best. But everything is pretty easy. It's very, very easy. So let's go ahead and look at this for just a second. All right, so Ohm's law. The V stands for voltage, the I here stands for current, the R stands for resistance. You can change the voltage when this cool sound, I guess, kind of sounds like you're being abducted by aliens. And you can also change the resistance. Doing those things changes the electric current. This is kind of what that would look like in an actual circuit. We will be building circuits online, which more on that later in just a second. I'm very excited about this. But we will be building circuits later in a different and better simulation. Oh, all the things, guys. Probably either later this week or next week. Almost figured out planning the rest of the semester. It's been fun. So yeah, you're just going to answer 10 questions about this. It's one page. Everything is easily checkable. A quick note about this. I do not care how long your definitions are. I don't even care that much if they're 100% correct. I do care if they're actually in your own words and not just copied and pasted from Google. And the reason I care is because I know what the Google definitions are. I wrote the PowerPoint. Like, why would I not know those things? I don't care if you let me just pause. Sorry. I didn't think of a right way to say this. It doesn't matter to me so much if you guys know the exact definitions of these terms, because I'm aware that you're probably really only learning them for possibly one quiz, and then they will be easily forgotten. I get that. I remember. What I do care is, do you have a vague notion or a way to remember this for yourself so that 5 years from now, if you are, I don't know, fixing a circuit in your home, if you're oh, the current, yeah, that's it's how much electricity is going through the wires. Okay. That's not entirely 100% as correct as the Google definition, but it's good enough that you'll kind of remember what's going on, what the relationship is years on down. Correctness is not as important as having a general sense of learning and concepts about the idea. That's the one I care about. So, don't copy and paste. Just put I don't know, a rough general estimate of just what you think those things are. After that, you're just writing, it looks longer, but I promise it's not. See, this is it. I listened to you. I cut it down. It's only 6 questions. I mean, a couple of them have parts A and B, but like, let's face it, it's just like, what are the symbols? And if you bring one up, then what happens to the other? Which brings us to our next thing, some vocabulary that I have used throughout the semester. Alrighty, on this post-it note, which I will soon have centered, we have the words direct and inverse. How to know if something has a direct relationship or an inverse relationship. Direct relationship, as you can see here, this is very hard to do backwards and on camera, means that things either increase together, they go up together as one thing goes up, the other one also goes up, or they decrease together. An inverse means the opposite. An inverse relationship means that as one thing goes up, the other one goes down. These are easy words to use when describing the relationships between things, specifically things like laws or scientific relationships in general, where you can just kind of quickly say, without saying that one thing causes the other, if things are related to each other. So the most common example, which we, I think, used at the beginning of the semester, is ice cream sales are directly related to number of crimes that are reported. And the reason isn't because ice cream sales cause people to commit crimes. Like, they're just so angry about the new Ben and Jerry's being out that they just go on like crazy crime sprees. Or even the opposite, that criminals just greatly prefer ice cream after they have like robbed a bank or something. It's just that both ice cream sales and crime rates go up when people are hot, because when people are hot, they are irritable and they also would like some ice cream. Makes sense. And that tangent is just one fun example of how you can use scientific knowledge to wow people. All right, there is like a teensy bit of math, very, very little though. The formula is as follows. Voltage is equal to the current times the resistance. And honestly, little cheat code, as you move one thing and you keep the other one kind of close, you can use this to check your answers. These on the side, you'll notice, look kind of like batteries. That's because that's what they stand for. More on that later. And let's see what else. Oh, okay. Yeah. So current is usually measured in amperes, but amperes it's kind of like watts when we talked about watts. Like, you guys knew watts was a units, but no one really uses watts when talking about just how many like watts are in things, because like a light bulb has 100 of them already. All right, like, you use a lot of watts. So the common subscription for it is milliamperes. A couple little notes. If you want to convert milliamperes to regular amperes, divide the number by 1,000. Here you'll get a number like 0.0, I think, 115. Divide that number by 1,000, and you'll get the correct answer there. All right. So that's it for this guy. Turn it in. Rubrics right here. The due date doesn't really matter as much. Try to do it when you can, preferably by the end of the week. That's the thing I would care about the most. Prioritize this assignment because it's for a grade over your other assignments for this class. Although I think on Wednesday and Thursday, we're going to finally do electricity in the human body, which is my jam, and I'm excited. All right, so everybody who has stayed here just to figure out what the assignment is, you can now hop off, go do that. For everybody else, we're just going to go through just a couple of slides, I promise, just explaining what this stuff is. Okay, not that one, not even that one. All right, it's like 3 slides, I promise. Hide this, put me in the corner. Okay, so Ohm's law tells us the relationship between voltage, current, and resistance. But what do those things really mean? Voltage is the potential difference between charge at 2 points. So charges flow, and this isn't just for charges, right? This is for all gradients, whether we're talking about charge or pressures or temperature. Things flow from areas where there's a lot of it to areas where there's only a little bit. Entropy says that things would like to be evened out. right? So things are always going to go from where it's high up and flow into areas of low. Voltage just says that there's a potential difference between 2 points. Like there's a lot of charge over here, there's not so much over here, so things would like to be moved between those 2 areas. Voltage is measured in volts, and we have a little V for our symbol. Electricity gets compared a lot of times to a water pipe because it's something that we've usually handled, either a pipe or maybe a water hose. And so people kind of get this a lot more intuitively. So if you have like a water hose, for example, or a water pipe, then voltage is like talking about the pressure of the hose. So things go from high pressure to low pressure. Voltage sources make sure that there's always a difference in charges between 2 different sections of a circuit. The 2 big examples for these are batteries and generators, both of which we will be describing how they work later on, either this week or the beginning of next week. Think of it how like a battery uses chemical energy in the form of electrolytes. You might recognize those from what Gatorade has in it. More on electrolytes when we talk about the human body and electricity. Electrolytes are chemical energies. Electrolytes are ions, all right? They have a positive or negative charge. They interact with each other in a battery, more on that later. And yeah, supply a current of which things move from negative to positive places, cathodes to anodes, and vice versa. Generators kind of do the same thing, except for where batteries use chemical energy to create this charge difference, generators use mechanical energy. Like if you got on a bicycle and had to power something, you would be a generator. Now, then if that's what voltage is, what's current? If voltage is the difference between 2 places and how much charge they have, then current is just the flow of that charge from one place to the next. Remember that only electrons can move. Protons are bound up in that nucleus. And in fact, if you remember back to our nuclear unit, the only thing that is moving those protons is like nuclear fusion in place of stars. So incredible heat and incredible pressure. That's the best you can do to actually do anything to the protons. We don't have that here on Earth yet, at least not in a commercial form. So protons aren't moving. Protons aren't moving here. Current's measured in amperes and noted with the symbol of I whenever we look at our equation. Similar to if I go back to our water hose analogy, then current is the water moving in the pipe. Now, both of those kind of sound like the same things to people. So think of it this way. If water flows from high to low pressure in a pipe, the thing that is moving is not pressure. It's just the water that moves. And we're describing where there's more water or where there's less water when we talk about pressure. Charge is kind of the same. So the current is the charge, those electrons, right, moving through the circuit. And voltage is how we describe, is there a little bit or is there a lot of it? Now, our next term, resistance, is futile. Just kidding. Resistance tells us something about how either the device that the circuit is the charge is moving through, or else the material that's being used, like maybe the wires that are being used, does that reduce the current any? Does that offer some resistance? So the current depends on both the resistance and also the voltage contained within that circuit. In a water pipe analogy, the resistance would be like the type of pipe or material used. Material with really low resistance is highly conductive. So metals have low resistance, high conductivity. Things like plastics, glass, wood, all have higher resistance and aren't very conductive at all. So resistance is usually the thing that takes up the charge or stops the charge from moving as fast as maybe it would like to. Sometimes resistance is a bad thing because it means that you're not getting as much current as you would like. But you need a little bit of resistance or else you get electrocuted. So not so much fun. Resistance is measured in a handy dandy little symbol called ohms, named after the guy who discovered it. Because when you find cool things, they just name them after you. It makes you wish you had a cool name. It's symbolized with this little character here, omega, which looks like I feel like it looks like the Lucky Charms marshmallow of the horseshoe, personally. And yeah, so more resistance, the flow is easy. Sorry, less resistance, the flow is easy. More resistance, it's harder to have a current. And this brings us to Ohm's law and all the handy graphics. Ohm's law, because it's a law, it's really just a math equation. Aha, welcome to laws. Tricky. Ohm's law tells us that the current is equal to the voltage divided by the resistance, or I equals V divided by R. In words, current in a circuit is directly proportional. Let me get my sticky note. Remember, directly, they go up together. Or inversely proportional, inverse, opposite ways, to resistance. So usually you see I equals V divided by R, that's Ohm's actual law, but it's rearranged a lot of times because we don't actually usually care that much about current. We usually care about what voltage we should get. So instead, you see it rearranged as V equals I times R a lot of times. These are the magic triangles. They just help you remember, oh, V is on top, that's I times R. V equals I times R. If I'm looking for I, then it's V divided by R because it's on top, V. If I'm looking for R, it's V divided by I. Here are the symbols, what we usually abbreviate them as, and then what they look like. Personally, I really hate how current is symbolized by an I measured in an amperes, and then that's becomes amps or A's. It's annoying. Well, now you know what Ohm's law is, and things are starting to make a little bit of sense. But then, what is power in this equation? If you remember from energy, power is the rate at which energy is absorbed or produced. It's a rate, right? So power when we were looking at our energy equations, was energy per second. How much energy you were using or producing per a unit of time. It's always measured in watts, but kilowatts or megawatts are also sometimes used. In this case, power actually also relates to Ohm's law too. Power is just the current times voltage. It's still measured in joules in this case. Sorry, that's not right. It's not measured in joules, it's measured in watts. See, I even had this fun Harry Potter meme. I know it's old, but I don't care. It's a gem. And over here's a couple things about how all those things relate to each other. Not just in a magic triangle, but in a magic circle. P is equal to V times I, but they rearrange everything for you and they tell you exactly what these things are equal to. So if you were looking for power, then any of these equations, if you had any of these two variables, you would be able to find the missing one, which is pretty handy. Okay, we're going to stop there because we're not doing magnetism. Couple of upcoming things. So we're going to talk about electricity in the body next time. I'm super, super duper pumped because I have all the things. How did that kid off of Jurassic Park not get electrocuted? What is electroshock therapy? And also, how does your brain and heart even function? How can you bring people back from the dead? This is the real Frankenstein level stuff, guys. We're going to get into it. And then also, I'm just really excited about this. And it's almost 11, so I have time. It's fine. Where's it at? Simulations. I found the most amazing virtual lab experience I have ever seen in my life. I might have passed it to every person I know who still runs a lab in college. And let's go down to circuits. I'm probably going to give you guys like as much access as possible to play with this as you would like. There's a lot of high school online labs, but there's also a bunch of college ones. So if you're into it, if you're into science, it might be something, I don't know, fun to do. They're pretty neat. And where's the circuits one? Ah, yes. We had to do the Ohm's law one, and they didn't have a more basic one. Behold, they're beautiful, and they only take 30 minutes to do. And look everyone, You can repair radios to contact scientists in Antarctica in real life scenarios. And also, you combine things like resistors and you make it work. And you know what? Where's the pictures? Ah, see? It's beautiful. Get your own little workspace. No more worrying about if you all have access to the same materials. Look at those graphics. Those are great graphics. That's right. We're getting jiggy with it. But you did have to know the equation first before you could. Okay, so that's why we're doing the equation today. We'll just ignore that. That's fine. This might actually be more difficult than I originally anticipated. But that's okay. And you can interact with your data pad. Super, super pumped. First, I was going to have you guys dissect squid neurons, but yeah, whatever. And so, yeah, with that, I went a little crazy. That's fine. So do the lab and the questions, and I'll let you know if I get the simulation pared down to a reasonable time limit. Have a great day.